Okay, take it away.
Great, thank you. Well, greetings from cold and snowy Illinois. Um, I'm grateful to the organizers for the invitation to give a basic introduction to KK theory. Okay. Okay, so to start with context, let's go with Atiyah and Janich independently uh, showed that if you have a compact Hausdorff topological space, then you can represent K-theory as homotopy classes of maps into the Fredholm operators on some Hilbert space. Atiyah defined an abstract elliptic operator on topological space X to be a bounded Fredholm linear operator between Hilbert spaces with an action of the continuous functions on X such that if you look at the commutator of t with multiplication by a function f, you get a compact operator. Right, so of course you're supposed to think that you have, say, a pseudo-differential operator of order 0, so that when you take the commutator with a function, you get a pseudo-differential operator of order -1, and hence a compact operator. And Atiyah showed that these elliptic operators surject onto the K homology of X, which he defined topologically by taking the appropriate dual of the space and then applying K theory. He left open the question of exactly how to describe these groups using the elliptic operator. So what relations should you be using? This was solved by two groups, so Brown, Douglas, Fillmore, and independently Kasparov. So BDF came at this by classifying short exact sequences where you have the compact operators, then a C-star algebra, and then the continuous functions on X. So here E is the C-star algebra. Kasparov first has a paper where he defines K homology, and then another paper where he describes how his theory relates to these extensions. And there he tackles more general extensions that look like this, where you replace the continuous functions on X with some C-star algebra A, and then the compact operators, you look at the stabilization of another C-star algebra B. So here A, B, and E are C-star algebras. And so ended up defining a bivariant functor, right? KK of A and B. So KK of complex numbers and then continuous functions on X, this gives us the topological K-theory of X, right? So from Atiyah, we can think of this as being Fredholm operators parameterized by X. If you put the continuous functions in the first entry and then the complex numbers, then this gives you the K-homology of X. So from Atiyah, we know that that should be thought of as elliptic operators, abstract elliptic operators on X. And so this suggests that we think of KK of C of X, C of Y as elliptic operators on X parameterized by Y. And indeed, if you're studying the family's index, then this is where a family of operators on the fibers of, say, a fiber bundle would live. So because the definition of the KK groups is a bit of a mouthful, let's do it in parts. So let's describe the typical elements of, say, KK, where we have C of X and then B with X a closed manifold and B unital. The usual assumptions for A and B is that the first entry should be separable, and the second one you want it to be, say, sigma unital. So here, let's say what a B is a C-star algebra. What's a B vector bundle over X? So this refers to a locally trivial bundle over X whose fibers are finitely generated projective right B-modules with B-linear transition functions. So for example, if B is the complex numbers, we just get complex vector bundles over X. If B is equal to the continuous functions over Y, then we get complex vector bundles over X cross Y. And if X tilde X is the universal bundle, the universal cover of X, and let's say that G is the fundamental group, and you take as B the reduced C-star algebra of G, then the quotient of the product by the group action is the universal C-star G bundle over X. So this bundle shows up a lot in approaches to the Novikov conjecture, things like that. Okay, so suppose we have two of these bundles. A B-elliptic operator refers to a bilinear elliptic IDO such an operator extends to a bilinear bounded map between suitable Sobolev spaces, right? These are examples of Hilbert B-modules, say E0, E1, and is B-Fredholm. Meaning that there is a decomposition E0 splits into E0 prime and E0 double prime, and similarly E1. D restricts to a map between these factors. This first one is an isomorphism, and these other two are finitely generated projective. This means that up to B compact perturbation, the kernel of D and co-kernel of D are finitely generated projective. And so then you can define the index. In this case, it's due to Mishenko-Fomenko. Right, so it would just be the formal difference of these finitely generated projectives. And it lives in the operator K theory of B. Okay, so here we mentioned Hilbert B-modules, so let's go ahead and say what those are. The Hilbert B-module E is a right B-module equipped with a phi-valued inner product. Right, which is right bilinear in the second variable. Satisfying, well, if you change the order of the elements you're looking at, you get the star in B. If you repeat an element, you get something non-negative in B with equality exactly when you have the zero element, and such that space we started with is complete with respect to the norm. That you get by taking this positive element of B, taking the norm in B, and then square root. Associated to E are the adjoinable operators, so and B star E. So these would be maps from E to E that are bounded and B linear and that have an adjoint. So there exists T star such that so of course we're used to working with spaces over the complex numbers where it's automatic that you have an adjoint, but in this generality it's not automatic, and so we have to specify that we're working with those. And within those are the B compact operators. Right, so this is the closure of the linear span of the rank 1 operators. Defined by so this gives you a closed two-sided ideal as usual. Okay, so that's some idea of what happens when we have continuous functions in the first entry and then a unitable B star algebra in the second entry. So one remark before the definition in general. So especially when we're used to index theory from Dirac type operators, we're used to perhaps having different bundles. But here and also there, it's standard to work with instead C2 graded spaces. So we would look at the sections of the direct sum as a C2 graded space and replace D with the self-adjoint operator. Also note that if D is self-adjoint and say has order 1, then T, defined as the bounded transform of D, has order 0. And satisfies the T squared minus the identity. So this would be just minus 1 plus D squared to the minus 1. That's, say, a pseudo-differential operator for order minus 2. And so in particular, it gives you a compact. That's true even if you're working with B elliptic operators. Okay. So with that in mind, a class in KKAB is represented by a Kasparov AB bimodule, right, consisting of C2 graded Hilbert B-module. B is a star homomorphism from A into the adjoinable operators on E and is even with respect to the grading. And T is an adjoinable operator odd with respect to the grading. It satisfies for any element of A that phi of a times t squared minus the identity, phi of a times t minus t star, and phi of a t minus t phi of a are all B-compact operators. Okay, so of course this reminds us of Atiyah's definition of an operator on a topological space. Right here, this comment, they will be working with self-adjoint operators. And then this is what replaces the Fredholm condition, right? So the phi of A is very useful because, for example, let's say you're working on a non-compact space, and let's say you have a complete manifold and a pseudo-differential operator, it's elliptic, then you have a parametrics, but the parametrics, even though it'll map improve Sobolev regularity, it's not going to be compact if you're in a non-compact space necessarily. So by multiplying by a continuous function with compact support, or even just vanishing at infinity, that's enough to get this error to be compact. So that's really useful. And this here just gives us some freedom. So this doesn't have to be compact on the nose. It's only has to be compact when you've multiplied it with elements of A. Okay, two Kasparov bimodules, AB bimodules. Are equivalent if and only if they're homotopic, meaning that there is a Kasparov bimodule with B replaced by B tensored with continuous functions on 0, 1, such that the two algebras you started with are what you get by evaluating KK consists of the equivalence classes and is a group with respect to the direct sum. Right, there's also KK1, which you can define in the same way, but using ungraded objects.
Sorry?
Yeah.
There's a question in the chat, namely, what you mean by equivalent here. I guess that the symbol 3 lines above.
I'm sorry, what do I mean by what?
With equivalent here, so at the last line that is shown now, at least on my computer, I guess there's an equivalent sign in the last line.
Yeah. So equivalent as so yeah, I guess equivalence of the Hilbert B-modules that takes the action to the action and the operator to the operator.
Yeah, we're just putting an equivalence relation on the set of all Kasparov AB bimodules.
Yeah, so I just mean you take somebody here and then you evaluate the function you have here at one of the endpoints, and you should get one of these.
Thanks. I hope this clarified the question.
Yes.
Okay, thank you. Okay, so for example, any homomorphism, well, star homomorphism, of course, between the C-star algebras yields a class in KK of AB. So here we take E to be just B plus 0, so that just means it's like an ungraded B, so everything's in the 0 spot. The inner product, this is B1 star times B2. The operator would be just 0. So the problem with taking 0, or what you should worry about if you take 0 as your operator, is that you need this to be a compact operator, be compact. So that means that if this is 0, we need phi of A to be mapping into be compact. But it's okay, because here the adjoinable operators would give us the multiplier algebra. And in there, the compact operators are just B. So phi of A is contained inside B, the B compact operators. If you start with the identity map from A to A, then this class is denoted just the 1 in KK-AA. Another example is if you have a differential operator or pseudo-differential of order 1 that's B elliptic, then you can take as your Hilbert B-module the L2 take as A the continuous functions and take as D the bounded transform of the operator. And this yields an element of KK CFXB, like we were discussing before. Okay, the real strength of KK theory comes from the Kasparov product. So this is a functorial bilinear associative product. Where we take KK of AB, a class in KK of BC, and we end up with a class in KK of AC. I'll denote it with a hash. Okay, so perhaps the most important example, or at least a motivating example. Suppose you have a differential operator of order 1 acting between, say, complex vector bundles. And then you have another vector bundle with a connection. Right? Then you can twist this operator with this vector bundle by means of the connection. So one way of stating this is that there is a unique differential operator for order 1 acting between E0 tensor F and E1 tensor F, such that d prime applied to a simple tensor section is going to be this whenever nabla f tau of x is equal to 0. Right? So if the connection evaluates to 0 at the point, then this operator is just ignore the tau and just act on the s at that point. Right? If D is a Dirac type operator, so just Clifford tensor with a connection, then of course all we're doing is replacing the connection with the so let's put E with the tensor product connection. D defines a class via the bounded transform in KK of C of X complex numbers. And similarly for D prime, this bundle F defines a class in the topological K theory. So here, right, so you would take the continuous complex ordered sections of F ungraded, and then multiplication and the 0 operator. But it also defines a class where I'll use double brackets when you also allow multiplication by functions on, right, so here there would have been multiplication by constants for this class, and for this class it's multiplication by functions. And then the class of the twisted operator is the class of the Kasparov product of these two. So notice that the class, the Kasparov class here, is independent of the connection, but to define the so it's independent of connection because it's equal to this product, right? But to define D prime, I made use of the connection, right? So that's something typical of Kasparov products, at least in practice. Right, so let me say something about that. So if you have the two Kasparov bimodules that you want to multiply, right? So say this is AB and this is BC, right? And then we want an AC bimodule, then clearly we should take as E, E1 tensor over B, E2. And phi should be just phi1 tensor, the identity the C adjoinable operators on E, but there's no canonical choice for T. Right, so the naive choice for T would be take T1 and then use the grading operator and tensor with T2. But unfortunately, usually this tensor product, the second term, is not well defined. Because T2 does not commute with B. And even when it is, it might not define a Kasparov B-module. For example, if you square it, you don't really expect it to get to be equal to 1. You'd expect it to be equal to 2 because each of these factors would square to 1. So you modify to so you'd multiply the first term by something and the second term by something with these adjoinable operators, and you'd want them to be positive and to sum of the squares to be 1. And these exist, but they are not easy to come up with. Their existence is known as Kasparov's technical lemma, which tells you all you want to know about it. In practice, what you do is more like guess and verify. So you guess what the Kasparov product should be, and then you check that your answer is correct. And you do that using a theorem of Conskandales, where they characterized up to homotopy, of course. Using an abstract notion of connection. So inspired by the previous example. Okay, so let's mention some examples that showcase the power of this product. So for example, the Thom isomorphism in K theory. If you have a complex vector bundle or a real vector bundle with a spin C structure, then the topological K theory with compact support of E is isomorphic to that of X. We can obtain a class alpha E in the KK of C0E, C0X, in case X is not compact. From the family of Dolbeau operators on the fibers of E. So to note that like that. And so this class is, you would take the L2 of E's on the fibers, multiplication by functions, and then is the class corresponding to this, but of course I mean the corresponding family of Dirac type operators. So d bar plus d bar star. And the proposition, which is due to Kasparov, but following, this is like a reinterpretation of Atiyah's proof. Says that multiplication by alpha E is invertible and implements the Thom isomorphism. If X is itself complex, I just mean a complex manifold, complex, then the classes of the Dolbeault operators on X, on E, and on the fibers of E satisfy that the class on the total space of E is the Kasparov product of the class on the base and the class on the fibers. Right? This is true more generally if, say, you had a fiber bundle of spin manifolds, then it's true that the class of the spin Dirac operator on the total space is equal to the Kasparov product of the family of Dirac operators on the fibers with the Dirac operator on the base, right? And that, again, tells you how much the notion of connection is wound up in this, because to compare the Dirac operator on the base with Dirac operator on the total space, you need some sort of connection to lift it to the total space. Okay, another example. Poincare duality. So Atiyah, when in his initial paper where he studies K-homology, he studied it using the Spanier-Whitehead dual. But if you have a smooth manifold, then the duality is now known as Atiyah duality. Well, without saying exactly what that is, the consequence is that he got an isomorphism between the K-homology of X and the topological K-theory with compact support of the cotangent bundle. Every class in K-homology in this case is represented by a pseudo-differential operator. And Atiyah showed that when you're looking at those, then this correspondence sends the class of P to the class of the symbol of P. He pointed out that this generalizes the Atiyah-Singer index theorem. And I'll say more about how it does in a moment. Kasparov showed that this too is a Kasparov product. Right, so note that the symbol defines the class. So it's in the topological K theory. So this would be KK of complex numbers and then C0 T star X. So continuous functions vanishing at infinity on T star X. But also a class. So just like for a vector bundle, we can change the multiplication to allow continuous functions, not just complex numbers. And then Kasparov's theorem is that the class of P is the Kasparov product of this double bracket class of the symbol with the d-bar operator on the cotangent bundle of X. So the cotangent bundle always has an almost complex structure, and we take the class corresponding to its Dolbeau operator. Let U be the inclusion of units. So this is a C star star homomorphism between C star algebras, so it gives us an element of KK. We get the analytic index of P by taking this Kasparov product, right? So we're just pushing forward from the manifold to a point, or if you like, we're just forgetting the multiplication by continuous functions, replacing it by just the complex numbers. Kasparov's theorem implies that this equals the corresponding product with this double bracket symbol class. But again, Kasparov product with this units just forgets the multiplication from complex of the continuous functions, replaces it with just the complex numbers. So when you do this product, you're just replacing the double bracket symbol class with the single bracket symbol class. So we end up with this expression for the analytic index. Okay, and so to see how this generalizes the Atiyah-Singer index theorem, let's discuss the topological index. So we get the topological index by trivializing the class of symbol of a pseudo-differential operator using an embedding. So we embed X into Rn. Let's let n be a tubular neighborhood. Right, so that X is going into n inside Rn. Right, n can be identified with the total space of the normal bundle to the image of X inside Rn. So we get corresponding maps of tangent spaces. A tangent space to Rn we can identify with Cn. And here Tn is a complex vector bundle over Tx. It's the normal bundle to Tx embedded in Cn. Since Tn including into Cn is an open inclusion, it induces a star homomorphism between the continuous functions vanishing at infinity of Tn and the ones on Cn. Right, so for example, if you have something with compact support in Tn, then it also has compact support in Cn, so you can just view it as an element of the other space. The topological index is the map where we start with a K-theory of the cotangent bundle, but using a metric, we can identify the cotangent bundle with the tangent bundle, so let's just say we're there. Then we can take Kasparov product with the inverse of the Thom isomorphism to end up in Tn. And then we can take Kasparov product with the class of J to end up in the topological K theory with compact support of Cn. And then we can take the Thom isomorphism, which here is just the Kasparov product with the class of the Dolbeault operator on Cn, and we end up in the topological K theory of a point, which is the integers. Right, and then the Atiyah-Singer index theorem says that as maps from the topological K theory of the cotangent bundle to the integers, the analytic index is the same as the topological index. And we can prove this by staring at the diagram. So, here, K point. Okay, so this is the route that we took to define the topological index. So we can fill in arrows here with the corresponding Dolbeault operators. And this triangle commutes just because Tn into Cn was an open inclusion, so this is just, this guy restricts to that guy. And then this triangle commutes because of what we saw about Dolbeault operators when you have a compact space, sorry, a complex space and a complex vector bundle. So from here, we see that the topological index takes a class and multiplies it with the Dolbeault operator on Tx, but we saw that from Kasparov's theorem, that is also equal to the analytic index. And I'll stop there. Thank you very much for your attention.
Thank you, Pierre. Let's all thank Pierre. Okay, are there any questions for Pierre?
Yes.
Zhao Ting?
Yeah. The last proof, it actually involves the associativity of the Kasparov product, isn't it? The proof of Atiyah-Singer index theory.
Okay.
Yeah. Yeah, that it involves actually, it's the essential part is the associativity of the Kasparov product.
I don't know if that's the essential part, but sure.
Okay, thank you.
Thank you for the question.
Somebody asks in the chat if there will be written notes available.
I'm happy to share.
Great. So then we'll make them available.
Sure.
Are there other questions before we turn off the recording? Okay, great. So then I'm going to stop the recording.